Well, thanks you all for sticking around. I know it's been a long afternoon of really some really fun talks, and it's really actually fun to be in between two academic professors. Nice now, because I actually did my PhD in physics at UT Austin, finished about 23 years ago. So I'm going to talk today about finding key influencers in Twitter networks that related to ISIS, and since we were talking about just now about the elections, we'll go to that example as well. Oh, that will go. Oh, there we go. There we go. Okay, so background information, just very quickly. As I said, a PhD in computational physics in pattern information and nonlinear systems. So the last 10 years, I've had my own little data mining startup company. It's been really fun to get to do that. So far, I've had on the order of 10 different clients. So the technology I've developed has been able to, it doesn't care what the nature of the underlying source data set would be, as long as it changes over time. So it's ranged from healthcare data to vehicle pricing analytics. Last year, I did some email analysis for a patent lawsuit. It's very interesting. I had to go to none of the data could leave their office, so I had to take a hard drive, do the analysis. They had 5 attorneys sitting around a table for 5 months, and in about 4 days I was able to go in and analyze tens of thousands of emails and find key examples that were helpful to their case. Also looked at mobile phone data analysis for another company called PlaceIQ. Retail Me Not, so looking at web analytics for online coupons. And there's a company called Vast that does a lot of work in terms of sales of used cars. So analyzed web user click patterns. So what are we doing? Basically, the idea is we want to use this anomaly detection technology to define the unknown unknowns. So obviously, in cases where you have human expertise and you know what you're looking for, you can use rules-based systems. Or in the case that Joydip just mentioned, you can actually, in some cases, you'll be able to generate those rules automatically. So the key advantage that we're finding here is that this is actually not really a machine learning approach. It's more of analysis and focus of attention mechanism. Now, we can certainly use it in conjunction with machine learning. I've done cases where I've done machine learning up front to create feature vectors that go into the anomaly detection. And I've also done cases where you do prediction afterwards. So they can fit within a machine learning flow, but it itself is not machine learning based. So we've talked about it. Obviously there are lots of existing methods that can be used and very effectively in different areas, but especially in cases where there really is never. What do you think about Facebook or Twitter? There's never a stable baseline, correct? So things are always changing, and because my approach uses techniques from chaos theory, it basically uses a way of being able to characterize how all these entities are changing over time. So in particular, trying to answer which entities' behavior evolved differently than others in the data set and which have shifted their behavior unexpectedly. And so we can simultaneously analyze the time evolution of network structures as well as any associated attributes. So if we're looking at text terms like NLP examples, it could be geospatial position, it could be prices. And because of that, we can find key players and detect, provide some early warning of unusual changes. So in particular, we're going to use something called finite time Lyapunov exponents. And I'll just say, I know it's late on our Friday afternoon, so you don't need to understand the details of this. If you're interested in the math, I'm absolutely happy to talk about it with you. Basically, what we do is for every cluster in the data set, we're going to represent that by a feature vector in a state space. And then as the system changes over time, that feature vector point is going to move within the state space. And what defines how that happens is what we call a flow map, and that defines the time evolution of the system. So Elise for short characterize the amount of stretching or contraction within the state space. So I should point out that Elise have been used in lots and lots of real physical kinds of problems. So chemical mixing, flow over aircraft wings, looking at ocean currents. So in a lot of cases, for example, when you're looking at fluid flow, we know what the Navier-Stokes equations are, and so you can do a lot of stuff analytically. In the case of like looking at ocean currents, you can have regular spatial grids, right? So you can do some numerical kinds of approaches there to estimate. But we don't know what the corresponding equations are for Twitter or Facebook or the stock market. So basically, this FTLE, a sigma down here, is proportional to the log of the square root of the maximum eigenvalue of this matrix product. Basically, when sigma is large, then the system is chaotic. If it's 0, it's going to be stable. And if it's negative, it's actually going to be converging towards a fixed point. Besides saying how much the system is changing, we can also characterize in what generalized direction. So I've done some examples for some potential partners where there were modeled computer users. And they said, we'll just see what your stuff can find. And there's this case where these fake users had like a normal day, and then they did stuff only around 3 in the morning, and then they went back to a normal day. And basically, because their behavior vectors changed in an unusual way, that is, they essentially in this state space split off, where I was able to just quickly notice that, and that wasn't a machine learning approach. It was just being able to look at the distribution of those Jacobian vectors. So some very interesting insights. And at a high level, this is typically how we do the analysis. We start at the representation of a particular timestamp. Typically, you break it up into clusters or segmentation. It kind of depends on the application area. If you need to resolve the cluster, is this a continuation of a previous one, or is this a brand new one? You can do that step. And then typically, these are very high dimensional data sets. And what we're going to do is reduce those to a lower dimensional representation. So I've actually, for example, looking at dynamics of social graphs, I had actually started looking at singular value decomposition. In that case, I actually found that it's too sensitive to small changes because it's very closely related to the underlying eigenvalue structure. So I actually came up with a new way that basically represents a directed graph as a modeled hologram. So that way it very smoothly changes. So if there are big changes, it will translate that, but you're not subject to these very wild swings. So once we have at least 3 time intervals, then basically I can start doing the FTLA calculations. And as I mentioned, from there you can actually you can connect these kind of results to pattern classifications or other kinds of predictive models. So we're going to step through 2 examples, pretty quickly. This is a Twitter set related to ISIS. This was right after the Paris attacks last fall. So about 2.5 million tweets. And what it did was, anywhere there are hashtags, URLs, or URL applies, create a generator network from that. And so do something called K-core decomposition to find the center part of the network, and then do anomaly detection, and also then from there be able to talk about detecting communities and topics and so forth. So in that particular case, the link types, you have people referring to websites, mentioning users, using hashtags, and so forth. And so once again, as I mentioned, I'm going to skip through the details right now, but basically we can use the K-core decomposition to find the center part of the network, because these are the truly the people who are best positioned to spread or share information. And so that's what that looks like. So basically you think about it like essentially a 23-layer onion, and the people in the center in the red are the ones who are best positioned to spread or share information. And we can look in detail to see who those are. In some cases, these are I included some hashtags as well: domination, CNN. There's one that says ban all Muslims, that hashtag that came up there. And then we can actually look to see, okay, what are the URLs that are in the center of the network? So show those. It's interesting, that first one. ISIS would love you to bomb them to bring about an apocalyptic final fight. So it's interesting to basically see what are the URLs that are most viral at the center of the network. And then I used an open source tool called Cytoscape. It allows you to visualize the networks in a very easy way. So we can actually click to see essentially within that central core who are some of the key players and what are the websites they're linking to. And once again, we can see who are the top users. So a lot of these are not too surprising. You know, David Cameron being Prime Minister of the UK, being towards the center. A lot of them are news outlets. This guy here, Tak Fatah, he's a journalist from Canada. And this guy, Yunus Algar, we'll talk about him in just a little bit. But so then the idea is we want to go from, great, lots of web pages. Well, how can we think, like distill down what people are talking about? And as Jason might be talking about later on, there are lots of very, very deep sort of NLP models that you can apply to that, latent and semantic indexing and so forth. What I decided to do was something fairly simple. Is basically, when you have a URL, you have the titles and the terms. I said, well, what if we just like create a path through using the order of the words in the titles, and then do a graph decomposition of that, so that there's basically all the titles and terms within those websites. So here you have, this would be the full title: Homeland Security Chair Obama covering up evidence ISIS is targeting refugee plan. And then basically what it had is then the words in that title would all be connected. And so by doing that, we can then group them into different topics of users and the websites so we can clearly see, exactly who are the sets of users connecting with which websites within a particular topic. And that's just another visualization of that. It's very interesting to see the different groups of users that might be tending to be some more central, center or right or left leaning, to see which websites they link to. It's some very interesting kinds of things. And then you can look, say, selected users based on the ones who are connected to a website. So sentiment analysis, we heard a lot of interesting stuff about that. Professor James Pennebaker is the head of UT's psychology department, and he and his research collaborators have a tool called, I believe they pronounce it Luke for Luke, yes. So I decided, well, what if we use that and apply it to, I decided not to, some of the folks have mentioned the problem of like analyzing a sentiment of tweets because they're so short. So I said, well, let's not do that. Let's actually just look at the sentiment of the web pages that people link to. And essentially what I did was I then focused on positive, negative, anger, and anxiety scores, and then essentially changed. So here we go, top web pages by anxiety score, right? So that had anxiety score of 11.11 there. And then same thing by negative emotions. Obviously, especially when you get into long web pages, you have both positive and negative words. So I thought, well, perhaps it might be useful to just look at the ratio of negative to positive. And so, like here, like Russian airstrike kills family in their cars, bombs obliterate ISIS oil convoy. So that was had the highest negative to positive emotion score. So then what we can do is then actually use those emotion scores as the weights, as the strength of those connections in the network. So when we see how the networks evolve over time, we can see where those emotions propagate within the network. And so basically the idea is this is a heat map that shows where this is the cluster within the network. This is looking as time goes on. So the red part here is where the hotspots of change are. And so once we know, when there's a particular hotspot, we can go back to the source data and see what caused that anomaly. And in particular, so this is looking at, going from early to late December, or the other direction, sorry, from early to late December. So this big red stripe here is a surge of Twitter user links to basically those websites with a high negative to positive emotion score. So that had the highest number of anomalies, ISIS trail of death, and that was that was the website. So the idea is, once again, we always want to go from here's the anomaly and go back to what caused that, because that way you want to be able to make it interpretable for the people who want to use the data. And once again, this is also, this is basically letting the data speak. We're not saying, I want you to search for all things that mentioned ISIS trail of death, right? This is just saying, let's look at the propagation of these emotions and then focus on the most unusual changes. There's a YouTube video of that, because we're short on time. I'll be posting a link to the slide. So it's kind of a cool animation. I don't know how many of you went to the graph day that was right after Data Day Texas, but Cambridge Intelligence came and spoke, and they have this awesome Keylines software. So I got a trial license for them, so I did a cool animation of that. So it was, check it out. And then just very briefly, I want to talk about some election-related tweets. So from February 24th to March 4th, so this is a sample of about 3.5 million tweets sent by 2.8 million users. And out of that, there are lots of things. 22.6 million generated links. And I actually did, for that day, I did the K-core decomposition every day, and then I focused on the center of the network. It turns out one of the, the maximum, I can't remember which day it was, had 88 layers. So that previous example we had, I think there were only like 30, on the order of 30. So I decided, well, that's huge. So I just really focused on, say, the top, the three innermost shells, basically. You can see, once again, who are the most, the best positioned and most influential users there, and what are they linking to. So top users, so obviously, a bunch of news outlets. So this guy Mitchell, VII, this guy Bill Mitchell, is a huge Donald Trump supporter, he says. Top URLs. Interestingly, this first one is about Texas. What's interesting to compare is, so we're looking at the URLs that are in the central core. If you look at the URLs that are highest by degree in the entire network, so that's that article there. If you look at the entire network, that one had 17,000 hits, and that was the John Oliver late night. So you can see if you just look at number of counts, you're going to see very different sets, right, of information. Right? There might be a lot of cat videos, right? So, which I absolutely love. So once again, we can do the same kind of community detection. In this case, there are 10 different communities. So I thought, well, let's look at the communities around each of the networks, each of these four candidates. Hillary Clinton here, that I just want to look at. Marco Rubio. There's Bernie Sanders. And there's Donald Trump's subnetwork within that. It's interesting to see who's connected most with those folks. So anyway, I hope that gives you a sense of the kind of applications this has in terms of social media monitoring. Obviously, there's a lot of interest in other areas entirely, like cyber defense and fraud detection and so forth. But I hope it gives you a little sense of the kind of research that I've been doing, and happy to answer any questions you have. Yes?
Yeah. One from my end, when I do these sort of open-ended analyses, is that validation and sort of evaluation of actually what you've come up with is very hard. In particular, you kind of have what you could call sort of the Albuquerque problem. If you're sort of like doing one analysis that's taking the next analysis, if this goes a little bit off, then the rest of it kind of goes off as well. So how do you control for that?
Well, that's true. I mean, the reality is there are very few sort of open source time-dependent data sets where there are known labeled anomalies. And in the case for that, then you can actually do kinds of things. Look at ROC curves and look at all the kinds of standard accuracy or precision metrics. So I think in a lot of cases, well, certainly for all the client work that I mentioned, the idea is, okay, of the sort of the top end anomalies that I show, is like how many of those ended up being useful to the clients. And fortunately, the answer was, and of course, I can't talk about them because they're specific to those clients. But fortunately, the answer was that they were. And in particular, a lot of these companies already had teams, internal data science teams, using more traditional machine learning approaches. And I definitely agree with Jordy that it's always a good idea. You don't use one method, you use an ensemble of methods. And the idea is hopefully this chaos-based method is going to find different types of insights than your standard deep learning or random forests and so forth. Yes?
So I see this as a perfect fit for like fraud detection.
Yeah, it should be very helpful for that. There's
Got
been
any traction with that?
Well, there's been a lot of interest, and then a lot of interest. Once again, the challenge is getting the source test data, but we'll see how those come along. Yeah.
How much do you play with graph construction? So you're saying like, well, somebody mentioned somebody, but often it's interesting to know that there was a co-mention kind of effect. So how much do you play around with how you define your graph?
Yeah. So. Yeah, basically it was like it is a directed graph, so you can have them go, have the links go both ways. Yeah, yeah, exactly.
I have several questions.
Yeah.
Could you spell the Cytoscape?
Oh, yeah. Oh, I'm sorry. I should have. Yeah. So I should have gone to the next slide. Next slide. Cytoscape.
Also, could you give me your patent number?
Yeah. It's Yeah, I think it was up at the top. Yeah. Yeah. What I'll do is, for the Meetup site, I'll add a link to these slides. It should be right here at the top. There we go.
Thanks.
Yeah.
And, so you're identifying a taxonomy, which is kind of like these communities, right? But I'm trying to understand, when you're using this anomaly, are you really talking about a discontinuity in the conversation that is like causing a bunch of activity? Is that what you're really ferreting out with this anomaly? Or?
Well, in this case, the feature vectors corresponded to basically, as I said, a modeled optical sort of holographic representation of all the interactions within a local subnetwork. So in this case, these were all user-centric ones. Obviously, I've flipped it around where I've looked at, where the center of the cluster is the URL. And then I've actually done it, even last year I did a talk on looking at the Ebola crisis. In that case, I actually, after I did the topic detection, I stepped up to topics to URLs and to see, okay, what were the most viral topics, because there was a surge of links to those topics. So it just depends on sort of what level you want the analysis to be. But in all those cases, that the feature vectors represent both the interconnections and the intensities of those interconnections. So, and I'm happy to give you more details too. All right, cool. Well, thank you so much for inviting me. Appreciate it.